Alright, the last thing that we have to actually look at in Physics 20 for dynamics is forces in two dimensions. Now, we've actually already talked about forces in 2D when we looked at inclined planes, because that required a deep examination of two dimensions. But what we're going to be doing this time is we're looking at more like resolution of forces, kind of like when we did 2D vectors in kinematics. So the framework that we're going to be using in this section, it's very similar to what we did in kinematics. You know, we could draw our vector diagrams, we can do the tip to tail, we can break down every vector, we can do all of that fun stuff. It's not changing. The only thing that we're changing, instead of words like displacement and force, displacement and velocity, we're probably going to throw in the word force. So the framework here is not going to change. So the first thing I want to look at is non-collinear forces. What we spent most of our time looking at are collinear forces, so forces in the same plane, we just add them up. Again, when we have things in two dimensions, we can't just add them. We have to start thinking about Pythagorean Theorem and such. So let's look at a real simple example of this. So we got two huskies. They're learning to pull on a sled. So one pulls directly west with a force of 250 newtons, and the other is going to pull directly south with a force of 310 newtons. So we want to determine the acceleration of a 125 kilogram sled. So if we want to get the acceleration, we know from Newton's second law, the acceleration is the net force divided by mass, which is good. What we need to do, though, is we need to determine the net force. Well, with this problem, first of all, it's a force problem. Let's draw a free body diagram. So my free body diagram, here's my sled. On this, we have one husky that's pulling west at 250 newtons. So we'll call that, let's call that force 1. So I'll say that's force 1. And then we'll call this sled, or this force down, we'll call that F2, 310. So this is kind of what our setup looks like right now. We have this F1 and F2. Now, what we've been doing a lot of is just kind of adding forces, but now with one going west and one going south, we can't just add those. These are in two different dimensions. What we can do, however, is we can draw a vector diagram. So our vector diagram, remember, with a free body diagram, all the tails of the vector meet at this dot. With the vector diagram, however, we're drawing kind of a vector addition. So we're going to draw the vectors tip to tail. So we're going to start with our first vector, this F1. So I'm going to just draw it here. So there's my F1. And then I have this F2. We're going to draw it starting from the tip of this previous vector. So then we're going to have something that looks a little bit like this. So then these are going to make a right angle. What we are interested in is we are interested in the net force, which is going to be acting along this line here. So that is going to be my net force. And then again, we're going to need an angle for this. So let's take the angle that's sandwiching my very first vector drawn and my resultant vector. So this net force vector, this is going to be my resultant. Now, because we already have a right triangle, this is really nice and quick to deal with. We can just use the Pythagorean Theorem, because we know that the magnitude of the net force, we know that's just going to be this F1 squared plus this F2 squared, and then square rooted. So we have our 250 newtons squared plus our 310 newtons squared, and then we'll square root that whole thing. And this is going to give us the magnitude of the net force. Now, again, for the moment, we'll ignore sig digs. It's not really what I'm looking for right now. So I'll just say that this is about 398.25 newtons. That works fine. What I need now, though, is I also need the direction, because force is a vector. So if I look back at my vector diagram, I have this angle here. I also know this side opposite to the angle. And I also know this side adjacent to the angle. I also know my resultant because I just calculated it. But again, try not to use calculated values unless you have to. Try to always use knowns to calculate something. So we know F2 and F1, they're directly given. So I'm going to use tangent to calculate this. So I know tangent of my angle, it's going to be that ratio of F2 over F1. or theta is going to be the inverse tangent of, well, F2 is that 310 newtons divided by 250 newtons. So in terms of an angle, this is going to give me, let's see here, if we punch that in, I'm going to get about 51.1 degrees. Now if I look at my vector diagram, I'm starting in the west direction and I'm starting to rotate towards the south direction. So this angle is 51.1 degrees south of west. Now all the hard parts have been done. We've done the trig, we've done the resultant calculation using Pythag, we've done the trig to get the angle, but we're not interested in the net force. We're actually interested in the acceleration. So acceleration also has a direction. The good news is the direction's taken care of. The direction of the net force is going to be the direction of the acceleration. All we have to do to get the acceleration, we're just going to divide our net force by the mass. So to get A, we know A is F net over M. So then we get that 398.25 newtons. The unrounded value in our calculator, we're going to divide that by 125 kilos. So we do something like that, we'll get about 3.19 meters per second squared. So that covers us for the acceleration. We got that from our net force, so we have the acceleration, we have our direction. So the last thing to do, we just kind of marriage the two pieces together. So we could say that for this dog sled here, the acceleration, it's 3.19 meters per second squared and 51.1 degrees south of west. Now, if you had drawn your vector diagram a little bit differently, let's say you drew F2 first, then you drew F1, you would have found the complement of this angle. So another acceptable answer for this would be 3.19 meters per second squared, and then the complement of that angle, we're going to have 38.9 degrees west of south. Both of those answers are acceptable. Whichever way you want to write it, go for it. I have a real habit just from when I learned physics when I was in Physics 20. I just had the habit I picked up from my teacher. We always drew our vectors in the x direction first, then we drew our vectors in the y direction. There's no reason you have to do that. It's just what's been ingrained into my brain. But you're free to do how you want it. There's no restriction on this.